Hello again, method students. In this video, we're going to go through the last exercise of chapter 14, which is on finding the sample size. So basically in this section, we're going to be looking at situations where you're given a probability, like often given a required probability, but you don't know the number of trials, and that's the thing that you're trying to work out. And so typically what we try to do in these situations is actually use our knowledge of binomials to create an equation that involves n, number of trials, and solve that equation in order to find n. A really good fact to keep in mind is this fact here, that the probability that, so in any binomial situation, the probability that x is greater than or equal to 1, so in other words, the probability that we get at least one success, is equal to 1 minus the probability that x equals 0. Because if you think about it, the only way that you won't get at least one success is if you get 0 successes. So that rule there is a handy one to remember. It often makes things easier. Okay. Let's check out an example here. Let's say that it's known, and this is made up, but let's just say that it's known that 10% of Ringwood Secondary College students write with their left hand, and a sample of students from the school is going to be chosen randomly. Okay. Part A of the question says, how many students would need to be selected in the sample before the probability of having at least one left-hander is 0.75 or more? All right, so let's do what we normally do and establish our variable to begin with. So let's let x equal the number of left-handers in this sample. Up here is our probability of success. This is our p value, so p equals 0.1. The question just says a sample of students is chosen randomly, and the question's asking us how many we would need to choose in the sample. So this is a situation where n is our unknown, but we are interested in making sure that the probability that we have at least one left-hander is 0.75 or more. So in other words, what we're saying here is that the probability that x is greater than or equal to 1 needs to be 0.75 or more. So it needs to be greater than or equal to 0.75. That's what the question's saying. Okay, so that's kind of establishing the information that we have. Now, if we look carefully at the probability that x is greater than or equal to 1, that's going to be really hard to represent when we don't know the sample size. And even with a calculator, we can't really represent this probability or calculate this probability because we don't know how many trials there are. So we kind of don't know how many successes to go up to. But what we do know is that the probability that x is greater than or equal to 1 will equal 1 minus the probability that x is equal to 0. Right? So 1 minus the probability that x is equal to 0 needs to be greater than or equal to 0.75. And this probability here is actually something that is relatively straightforward to express in terms of n. All right, so let's use what we know about binomials here and say, okay, well, 1 minus. The probability that x is equal to 0, if we want no successes, it means that we want all failures. We want every student in this sample to not be a left-hander. Right? Now, the probability that any one student is not left-handed is 1 minus p, so it's 0.9. And if we want that to happen over and over and over again for the full sample, well, that would be to the power of n. In other words, the probability that x is equal to 0 is 0.9 to the power of n, because we would just want to get every person in the sample being a right-hander, and the probability of that is 0.9. Right, and we want that to be greater than or equal to 0.75. Right, now this equation here, still pretty messy, but if this is a calculator question, well, we've done all the hard work now because we can just chuck this into our calculator and use solve. And that's exactly what I'm going to do. So, action advanced solve, 1 minus 0.9, up to you whether you want to use n or just use x. I'm going to use x. Needs to be greater than or equal to, so your inequality symbols are in math 3 on your keyboard, so it needs to be greater than or equal to 0.75. And we get x is greater than or equal to 13.157. So, n needs to be greater than or equal to 13.157. Now, n is the sample size, right? We can't go and interview 13.157 people, so n needs to be a whole number, which means for n to be greater than or equal to 13.15, it actually needs to be n is greater than or equal to 14, because if n was 13, our probability wouldn't quite be high enough. So this is a situation where you actually have to go up to the next whole number. It's not rounding to the nearest number. And so I guess to answer the question, well, how many would need to be in the sample? We would need at least 14 students to ensure that the probability that at least one student in our sample is 0.75 or more. Okay, Part B, this question says, how many students would need to be selected before the probability of having at least 2 left-handers is 0.75 or more? So really similar question, but this time we want at least 2 left-handers in our sample. So what we're saying is the probability that x is greater than or equal to 2 needs to be greater than or equal to 0.75. Now you would expect that this means we need a bigger sample, right? If we needed to get 14 students before we had this probability of getting at least 1 left hand in the sample, if we now need at least 2, you'd think we're going to need more students in the sample. So we were expecting a higher number than the 14 we got in part A. Now this is a trickier question, but we can set it up the same way and say, well, if we want at least 2, the only way that we don't get at least 2 successes is if we either get 0 or if we get 1. And so we can say that this is really 1 minus, oops, I forgot the 1, 1 minus the probability that x equals 0 minus the probability that x equals 1. That is equivalent to the probability that x is greater than or equal to 2, and that needs to be greater than or equal to 0.75. Okay, so really what we've just done there is equated this to this. Now, we already know from the previous question how to represent the probability that x is equal to 0. That's just 1 minus 0.9 to the power of n, right? This is where we want all failures. We want all non-left-handers. This one's a little bit trickier. The probability that x is equal to 1, well, that means we want 1 success, right? Now, we have n, remember that we have n trials, and the probability of success is 0.1. So what this is saying is we want n trials with 1 success times by 0. Oh, I've mucked it up. I probably should have put the 0.1 first. So let's put 0.1. Sorry, that's a little messy. We want 1 success, right? So we want 1 left-hander, so 0.1 to the power of 1 times, and the rest of them we want to be failures, 0.9. So we want all of our trials except 1, right? So that's to the power of n minus 1. This is saying that the number of right-handers we're going to get is everyone in the sample except for one of them, right? So that is the way that we can use the binomial formula to represent each of these 2 probabilities. And remember that we still want all of this to be greater than or equal to 0.75. And we can actually tidy that last bit up a little bit. So 1 minus 0.9 to the power of n minus. Now, n choose 1. If you want 1 success from n trials, well, there's actually n different ways that can happen, right? For example, 10 choose 1 will be 10, 20 choose 1 would be 20, 100 choose 1 would be 100. So this is actually equal to n. So this is n times 0.1. So I'm going to write that as 0.1 n times 0.9 to the power of n minus 1, and all of that needs to be greater than or equal to 0.75. Now, it still looks messy, but we've got it to the point where we can actually get the CAS to do it for us. So let's pop that into the calculator. We're going to solve 1 minus, let's see if we can get that looking a bit nicer for you. It might be easier to see the screen. 1 minus 0.9 to the power, again, I'm just going to use x instead of n, minus 0.1x times 0.9 to the power of x minus 1. Right, and we want all that to be greater than or equal to 0.75. Oh, all right, and what's happened here is the calculator just seems to have given me back the same equation I just typed in. Right, we don't want that. Every now and then when you're solving an inequality, the CAS does seem to struggle a little bit if it's a really complicated one. I was going to see what happens if I change my inequality sign to an equals sign. More solutions may exist. Okay, it's actually giving me a value here. So this is okay because we know that it's a greater than or equal to situation. So we know how to interpret our answer. Now, -8 is definitely not going to be our sample size, but this 26.065, that looks like a realistic answer. So we've got, as a solution to this inequality, n would need to be at least 26.065, right? And again, like in part A, this actually means that as a whole number, n needs to be 27 or more in order to make sure the probability is above 0.75. So we would need 27 or more students in our sample before we can be sure that the probability there's 2 or more left-handers is greater than 0.75. Right, so that's a pretty tricky question when it's greater than or equal to 2. When it was greater than or equal to 1 in part A, not so bad, right, because this part was not too hard to set up. What made that question a bit trickier in part B was this probability that x is equal to 1. But you can see that it's just an application of our binomial formula here. Now, there is a bit of a shortcut way, which I want to show you on the CAS. It's a bit of a trick, but I think it's a good one. The difficulty with this one though is that it's kind of hard to show working out. So if it's a 2 or 3 mark question, you might have to bite the bullet and go with this method. But if it's multiple choice or something like that, you can actually use trial and error with Binomcdf. Right, and I'll show you what I mean by that on the calculator here. So this question was saying, if we're redoing part B, that we wanted, well, we didn't know the sample size, right? But we wanted we were interested in having at least 2 left-handed. So let's go interactive, distribution, discrete, and binomial CDF. So if we wanted at least 2 successes in our sample, then the lower limit would have to be 2. The number of trials is the one we don't know, and the upper limit, therefore, we wouldn't know either, right? The probability of success, we did know, that was 0.1, because there was 10% of people were left-handed. Now, I've called this a trial and error method because let's just say that we had a sample size, in our head, we just thought maybe 10 people will be enough, right? So we said, imagine there's 10 people in this sample and we want at least 2 of them to be left-handed. So we'd put it in like this, and the calculator would tell us that the probability of getting 2 people or more out of 10 is only 0.26. Remember, we want this probability to be 0.75 or higher. So we're obviously going to need more than 10 people to make this work. We could try, I'm just going to copy it down so I can change the numbers. Let's say, okay, well, maybe we want, we obviously need more people. Let's go to 15. So see, I'm not going back to the interactive screen. I'm just going to change the numbers in the main screen. Okay, if I make it 15 people, the probability of getting 2 or more is 0.45. Remember, we need to get it to 0.75 or more. So you can see this is just a trial and error method. Let's go to 20 people. Okay, 0.608. So I'm getting closer, right? And then I might go 25, 25. Okay, 0.728. So I'm getting really close. Remember, it needs to get over 0.75. So you can see how this is just a trial and error method. So once you get pretty close, you might just go up by 1. So if the sample size is 26, I'm almost there, but not quite. If the sample size is 27, we get over the 0.75. So that's the first whole number that gives us the probability that's greater than 0.75. So you can see that sort of trial and error method, particularly once you've done it a couple of times, is going to be a fair bit quicker than setting all this up. The catch is just if it's a 2-mark question or a 3-mark question, you have to show working out. It's kind of hard to show working out for this trial and error method. But in a multiple choice question, that can be really handy because you can just test the 5 options that you've got using the different numbers of trials. So bit of a tip there. Hopefully you find that one helpful. Anyway, good luck with exercise 14C. As always, get in touch with your teachers if you need some help or if you've got any questions about this video. Otherwise, it's bye for now and see you next time.